right, so these are rules for oxidation numbers. Oxidation numbers are fairly important for us when we talk about the transfer of electrons. So it's all about electrons and in an atom. So electrons moving from one element to another. And this could happen either in a bond where you have an uneven pulling of electrons due to electronegativity. Ionic bonds, you see the negative and positive side. This can also happen in a reaction though. And this is eventually where we're going to go with these oxidation number rules. So let's start with number one. So number one is the elemental form is always zero. And what does that mean? So I'm going to give you two examples of elemental forms. I'll make them A, will be things like metals, as solids though, not as ions. So for example, when you have something like sodium as a solid, or magnesium as a solid, or even a metal that is transition metal, such as copper as a solid, and even something towards the right side of the periodic table, which is aluminum, which is a solid. These are all zeros, meaning that if they're solid, they're one metal sharing their valence electrons with other of the same metal. So pure aluminum, pure copper, pure magnesium, pure zinc, pure silver and gold, they all have an oxidation number of zero, as long as they're in their solid form. As soon as they become an ion, they're no longer a solid form, and therefore they could even be a salt, and they're not going to be a zero anymore. So what's the other one? The other one are some gases. So 7 be exact, 7 gases. And these gases are, in order from left to right on the periodic table, H2. So hydrogen as a gas. Then the next one will be nitrogen as a gas. Then oxygen as a gas. Then fluorine as a gas. Then we'll go down column 17 or 7A, which will be chlorine as a gas, bromine as a gas, and then iodine as a gas. That should be 7, right? 1, 2, 3, 4, 5, 6, 7. Yeah. So these are H2 is in column or row 1 and column 1, but N2, O2, and F2 are all in row 2. They're fairly simple. All gases bonding together with the same element. Therefore, when they share electrons, and I'll just do an example with a Lewis dot structure here. So when this hydrogen is sharing its one electron with another hydrogen, and this goes for any of these, they're sharing equally, meaning they pull on the electron with the same force. And remember, the number that we give them, in this case 2.1, are the electronegativity numbers. So this one hydrogen on the left is not going to pull on the electron any more than the hydrogen on the right. So therefore, either hydrogen has one proton and one electron. And therefore, those two charges, one positive, one negative, make an oxidation number for each of these. I'll do it. Let's go purple. Each of these are going to be zeros, meaning that they have one proton, one electron. They are not pulling an electron in any direction, and they're going to be zeros. Some of these, though, like they can have double bonds and triple bonds. So, for example, oxygen, on the other hand, has a double bond with another oxygen. Let's put in those unpaired electrons. Put 2 there and 2 there. 2 there and 2 there. And neither one of these are pulling on the electron any more than the other, even though they have a very high electronegativity of 3.5. But since they're both 3.5, one is not going to, remember, oxygen has 8 protons, 8 electrons. One is not going to pull on electrons any more than the other. All right. So that's the elemental forms. let's go with rule number 2. Ooh, let's go, try to go red, be consistent here. So rule number 2 says that oxygen is always, I should probably say almost. So let's do that. Almost always -2. Right? So if oxygen is almost always -2, when is it not? Well, we see right above when oxygen is with another oxygen. There's one other exception when oxygen is in a compound called hydrogen peroxide, but you're not going to really see that. So let's just assume oxygen is always a -2. And when does this happen? Well, let's take a look at an example. And again, Lewis dot structures are the best things to look as for example. So you have hydrogen bonded to an oxygen. We're doing water here. Bonded to a hydrogen, 2 unpaired electrons down there, another 2 down there. And remember, I just gave you those 2 electronegativities, 2.1, 3.5. We could definitely see there's going to be a pull towards or in the direction of our oxygens. So this electron is going to be pulled down that way. This electron is going to be pulled down that way. So even though oxygen normally has 8 protons, 8 electrons, in this case, with the pull being so strong with those 2 electrons, 1 from either hydrogen, now we're going to have 10 electrons and only 8 protons. So not surprisingly, this is going to be a -2. Therefore, this hydrogen losing electron is going to be a +1, which we'll get to a rule a little bit later. So that oxygen is a -2 because it doesn't have equal numbers of protons and electrons anymore. I want to skip one, which I missed. I probably should have done before this. We'll call it rule number 3. We're going to say ion charge is equal to the oxidation number. Oxidation number can be abbreviated O.N. So, all right, let's take a look at this. So if we remember our ions, we have ionic bonds. So let's take a look at something that we know is an ionic bond, such as NaCl. And this could even be a solid piece of salt, but we know that the sodium is going to be a plus or maybe a 1+, and the chlorine is going to be a 1-. If you notice where the charges are, they're on the right side of the number. Those are ion charges. The oxidation number, though, is going to be +1. Let's make this red. For sodium is going to be +1, and for the chlorine, it's going to be -1. So we take the charges and we just move the sign onto the other side. And take a look at something else. Let's take a look at another ionic compound. Let's put some multiples in here. Let's look at something like iron oxide. All right, so we'll go 2 and 3. So what are we going to have here? Well, we know the charge of oxygen is a -2. Oxygen's a nonmetal here. The Fe is a metal. So when you have nonmetals and metals, you have charges usually. So this is going to be a -2, and therefore this is going to be a +3. And if you're not sure how to figure that one out, I'm going to multiply. So 3 times -2 is a -6, and that 2 times the +3 is +6. So the +6 equals the -6. Therefore, the oxidation numbers are iron +3, oxygen -2. Oxygen likes to gain 2 electrons. Remember, it's 2 away from being a noble gas, and that noble gas is neon. Iron, kind of weird transition metal. It's kind of hard to sometimes figure out. All right, so that is rule number 3. Let's go rule number 4. Rule number 4, kind of like the one with oxygen, we'll go fluorine. So fluorine has the highest of all electronegativities. So again, is almost always, because there's never an always in chemistry, -1. And the reason for that is because of that electronegativity. The only time it's not, and we'll go back up to here, is you see this fluorine right there. It's an F2. That means there's two fluorines sharing electrons equally. They both are pulling on the electrons, so that's going to be 0. But in almost any case, if we put sodium fluoride, let's go with, if we go sodium fluoride, all right, well, sodium is going to be +1, and fluorine is going to be a -1. I probably should have put that in first, fluorine, if this is always a rule with -1. Let's do another one. Let's do another one such as, what could we do? How about calcium fluoride? And in this case, there's going to be 2. So the fluorine is a -1, and there's 2 of them. Therefore, that calcium's got to be a +2. So fluorine is almost always in -1 because of the electronegativity, the pull on the electrons. I just showed you ones, this one should have been an Na, sorry, sodium fluoride. But let's show you one where I'm not putting a metal with the fluorine, and say I give you something like, let's go with something like sulfur. So you get sulfur with fluorine, and there's 6 of them, 6 fluorines. So this could tell me that, well, fluorine's almost always a -1. So there's a -1. Multiply it by the 6 gives me a total of -6. Therefore, 1 sulfur, it's got to be a +6 because the totals have to equal 0. So very similar to what we did earlier in the year with the ions getting to 0. The same thing happens with the oxidation number. So let's go with another page. There's only 2 more to go. And the 2 will be pretty straightforward. One is going to be about hydrogen. I mentioned it, I think, with when we were doing the oxygen and the H2O. So for the most part, those are the biggies, but the last 2, still very important. So number 5 is hydrogen can be a +1 or a -1. Now it depends on the element that it's with. So for example, our H2O, our hydrogen was a +1 because it was with a stronger water, meaning water had a higher electronegativity. Let's take a look at something else. Let's take a look at carbon with the 4 hydrogen in it. Well, if we take a look at a Lewis dot structure for carbon, 1, 2, 3, and 4, and you have the hydrogens coming out over here, here, and here, and the 1 valence electron that hydrogen's going to share and has, well, what's going to happen here is that there's going to be a slight pull. Let's use in green. We know these hydrogens are each 2.1. In terms of electronegativity. We can look that up if we need to. Now carbon is 2.5, so it definitely pulls in the direction of carbon. It's only a slight pull, but still enough, and that happens for each of these. Each of these. And what happens here? Well, in this case, the hydrogens become a +1 because they're losing that 1 electron, sometimes slightly, to carbon. And these carbons are going to be a -4 because they're going to gain 1 from each of those hydrogens. So this is a situation where the hydrogens are a +1. Let's talk about where a hydrogen is a -1. -1. You don't see this too often, but let's take a look at one. How about sodium hydride? Now sodium, if we were to do a Lewis dot structure for this, 1 dot there. The hydrogen, 1 dot there, right? So what's going to happen here? Well, let's put in some electronegativities. 2.1. In this case, the 0.9 for sodium means that sodium is weaker in terms of its electronegativity, which means in sharing of an electron, this is going to go over to the hydrogen. Hydrogen is going to be the negative this time, and sodium is going to be the positive. And going to be a positive by 1. So normally we see hydrogen being a positive, but it's when it's with certain metals, especially metals that are on the left side periodic table columns 1 and 2, you're going to see a negative And then finally, number 6. Oxidation numbers should add up to, should add to 0. Unless noted. All right, so what is that going to mean? Well, in H2O, all right, when we looked at our oxidation numbers, we had the -2 of one oxygen and the +1 of each of those hydrogens, and they, when you do the multiplication of the 2 times the +1, you get a +2. They add up to 0. When you have the, let me give you one that we haven't seen before. How about copper? Copper sulfate. All right. So in this copper sulfate, I know, let's do some different colors here. I know that each of these oxygens are -2, so that's -8. I know that copper, in this case, because we know sulfate's a 2- overall, and there's only one copper, so this has got to be a +2, and there's only one of them. So I'm going to add another +2 at the top because I'm going to add these, and they better equal 0. So what am I going to have to add? What does sulfur have to be in order to have a -8 and a +2 make 0? Well, it's got to be a +6. And since there's only one of them, that sulfur gets a +6. All right. And I use this for a reason, because remember how I said sulfate was a -2. So these are the oxidation numbers, the ones right above the elements: copper +2, sulfur +6, oxygen -4. But let's take a look at just the sulfate, SO4. And this is where we see that this is a -2. So that means that the totals better add to -2 in this case. So let's do it again. We already saw that each of these oxygens are -2 for a total of -8. The sulfur is going to be a +6. And of course, they better add up to -2, because that's what this charge is telling me. So this is where unless noted comes into play. So most of the time, if you don't see a charge on a compound, it should add up to 0 for its oxidation numbers. But in this case, it's going to add up to -2 because there is a charge for this polyatomic anion. So I hope the rules have been helpful in terms of understanding how we apply these oxidations.